In this video, we're going to discuss how to solve rational inequalities. So the word rational comes from the word ratio, which means we're going to have expressions that are fractions, and the variable might be in the numerator or the denominator or both. And if we think about the graph of our rational functions, and we think about where the function might change sign. So one side of the inequality will be 0, just like we had for our polynomial inequalities. One side is going to be 0, and so we'll be saying that this rational function is greater than 0 or less than 0 or something like that. So we're interested in where's the function positive and where's the function negative, just like we were for polynomial functions. So the function, a rational function, can change sign at the x-intercept, just like our polynomial functions changed sign at the x-intercept. It's positive on one side, negative on the other side, potentially. Some x-intercepts, it won't change sign because it might just touch the x-axis and turn around and go back in the same direction. But we definitely need to at least see what's going on either side of the x-intercept. And then with rational functions, there are other possible places where it can change sign besides the x-intercept. So for example, if we have a hole in one branch of the function that lands right on the x-axis, then the function might be positive on one side of the hole and negative on the other side of the hole. So any place where we have a hole in the graph, we'll need to inspect. And then the function could change sign at a vertical asymptote as well. For example, this function is negative on the left side of the vertical asymptote and positive on the right side of the vertical asymptote. So those are the three things that we need to look at: is our x-intercepts, our holes, and our vertical asymptotes. Now, our holes and vertical asymptotes are going to come from when the denominator is 0, so that means any x value that makes the denominator 0, we're going to need to use that number to split up our intervals. And then for the x-intercepts, we know that an x-intercept is a point where y is 0, and so that means if we plug a number in for x, the function value is 0, and in the case of a rational function, the only way we can get 0 is if it's 0 over some non-zero number. So to find our x-intercepts, we need to know where the numerator is 0. So we'll set the numerator equal to 0 to find out where our x-intercepts are. We'll set the denominator equal to 0 to find our holes and vertical asymptotes, and those are all the numbers that we'll need to split up our number line and then check the intervals for where the function is positive or negative. So here's our first example. We have x plus 2 over x minus 5 is greater than 0. So the solutions will be numbers that we can substitute for x that will make the left side positive. And we know that an x value of negative 2 makes the numerator 0. So that will be the location of an x-intercept. And then an x value of 5 would make the denominator 0. So that's the location of a vertical asymptote. So those are the two potential places where the function might change sign. The function doesn't necessarily change sign there, but we need to check and see if it does. Now, one thing that we also need to keep in mind is we need to think about whether those two numbers themselves are solutions or not. Well, if we substitute in 5, we get 7 over 0. We can't say that that's greater than 0 because that's not even a number. So if an x value makes the denominator 0, it's definitely not going to be a solution, because if you don't get a number, you can't compare it to the other side, and it's not going to be a true statement. So anything that makes the denominator 0 is not a solution. In this case, if we put in negative 2 for x, we get 0, of course. We already established that. And so in this case, since it's a strictly greater than, this is a false statement. 0 is not greater than 0. If we had a greater than or equal to, then negative 2 would be a solution, but it's not in this case. And so then just like we did for our polynomial functions, we need to substitute a number in each of these 3 intervals and test it and see if we get a true statement. So I'll do 1 just to show. So if we put in negative 3 for x for the far left interval, then we get negative 1 over 2. So negative 1/2, which is not greater than 0. So that's a false statement. So that means we do not have any solutions there. I'm sorry, I made a mistake there. That's not supposed to be a plus 5 on the bottom. That's supposed to be a minus 5. That makes a big difference in this case. So we get negative 1 over negative 8, which is positive 1/8. So actually, negative 3 is a solution because we got a true statement. So all of the numbers on this interval are solutions because we got a positive number. If we substitute in 0 for x, we get a negative 2/5, which is not greater than 0, so we don't have any solutions there. And if we substitute a number greater than 5, we get a positive number. I'm going to skip the details on substituting some of these numbers in. So we have solutions to the left of negative 2 and to the right of 5. So we would write these solutions then in interval notation, not including the negative 2 or the 5, because we already decided that they are not solutions. All right, here's our next example. We have x minus 5 over x squared plus 3x minus 10 is less than or equal to 0. So the solutions will be numbers that make the left side either negative or equal to 0. So to split up our number line, we need to see where the numerator and denominator are 0. So we know that the numerator is 0 when x is 5, and we'll need to factor that denominator. So that denominator factors this x minus 2 times x plus 5. And so 2 and negative 5 would be our numbers of interest there. So we have 1, 2, 3, 4 intervals to check. But before we do that, let's think about those 3 numbers we put on the number line. So 2 and negative 5 are not solutions. If we substitute them in the left side, we get something over 0, which is not a number. And if it's not a number, it can't be less than or equal to 0. So like I said in the last example, if it makes the denominator 0, it can't be a solution. Now in this case, if we put 5 in for x, we get 0 on the left, and 0 is less than or equal to 0 since we have that equality included now. So 5 is a solution for this one. So then we'll test a number in each of the 4 intervals. I'll omit the details there. If you substitute something in the first interval, it becomes negative, so those are solutions, since we're looking for less than or equal to 0 here. The next interval, everything's positive, so no solutions there. This interval, everything is negative, so those have solutions, including the 5. And then positive here, so no solutions there. So the solutions would look like this in interval notation. So including the 5, but not including the 2 or the negative 5. We'll do one more example. Here we have x plus 2 over x squared plus 6x plus 9 is less than 0. So we'll need to factor that denominator. If it's possible to factor the numerator, you would factor the numerator as well so that you can see where it's equal to 0. In this case, the denominator factor is this x plus 3 times x plus 3. So the only number that makes the denominator 0 is negative 3. It will not be a solution because if we plug it in, we don't even get a number. And then the only number that makes the numerator 0 is negative 2. And this will not be a solution in this case because we would, if we substitute in, get 0 less than 0, which is not true. So then we have 3 intervals to test, so we choose a number in each interval, substitute in the left side. We get a negative number for this interval, negative for this one, and positive here. And we're looking for it to be less than 0, so the negative ones will be where our solutions are. So here and here. And then we'll write the solutions in interval notation. So that hole at negative 3 splits up our solution set. We have to be sure not to include it, so that's why we still need a union of intervals here.